Hi, everyone. Thanks for joining me today. I'll continue with yet another clickbait title. And a few words about me. My name is Philip. I'm Kotlin libraries team lead at JetBrains. And besides working on many other libraries, like standard library or, I don't know, like Kotlin X coroutines, I am also Kotlin X I/O maintainer, the library about I/O, as you can guess. And because of that, the place where leaking abstractions, data races, and security vulnerabilities all meet, for me, is file systems. But how did we get there? Here's a very quick and brief history of file systems. First, file systems emerged in the 1950s. Those were simple, flat file systems allowing you to organize all data in a linear space, which looks like my desktop directory on laptop. Then amount of data started growing, and by 60s, first hierarchical file systems emerged. And fast forward into 2026, those are almost the same file systems, at least conceptually, that we are using today. So doesn't that mean that after all these 60, even more years of development, file systems are mature, their APIs are stable, and are easy to use? Well, let's check it. And to check it, let's implement a part of my pet project, imaginary pet project. And that would be a simple REST controller that gets a username and fetches an image corresponding to this username from an image store. And because it's all about file systems today, we will cache these images on a local file system. And of course, it's 2026. I will not write all the code myself. Instead, I will generate it using an LLM. And I will do for two reasons. First of all, it's something that everyone uses today. And the second reason, and most important for me, is because LLMs are kind of overaging over existing code bases. So the code it will generate will resemble the code that actual developers wrote in their repositories some time ago. And here's my prompt. I asked an agent to create a Kotlin REST controller that, first of all, accepts a unique username, then loads an image from a database for that user, and returns it. And to make the controller faster, I asked it to cache images on a local disk. And a few words before we'll take a look at the actual code. Spoiler, it runs. There are no silly typos we will laugh at. It uses a particular file system API, but it could be any other. It doesn't really matter. It's not the point of this presentation. And let's not focus on the code itself, but rather review the logic first, and then we will go to the code and see the details. And speaking of logic, it's pretty simple. First of all, there's some initialization. We receive a user image repository, which allows us to access a database with images. Then we initialize a cache directory, the place where we'll cache images. And then, for some reason, an agent generated a base64 encoder, and we will talk about it a bit later. Controller itself accepts a username, encodes it into base64 string, and then infers a file name within the cache directory using this string. If the file exists, it reads its contents and returns to a user. Otherwise, it makes a request to the database, loads an image from there, writes it back to the cache, and returns to the user. Everything pretty simple so far, nothing red. And as I said, it runs. So I asked my friend to test it. Friend of mine, they sent a request. Unfortunately, requests took some time to finish. And also, unfortunately or fortunately for me, a friend of mine decided to send one more request because they decided they don't want to wait anymore. They sent the same request once again, and this time things worked much quicker, and they got a response, but unfortunately they received a corrupted image. Why that happened? Well, that's because there is a race condition, and it's a race condition between the part where we're reading from cache and the part where we're writing into the cache. And here how it works. When the first request arrived, it checked that file does not exist in the cache and started writing the data loaded from the database into it. At the same time, the second request arrived, it checked existence of the same file, and this time the file existed. So it started reading it. And unfortunately, because the first request not finished writing yet, it read only partial data, and it was corrupted. That's a race condition. There are many different ways to fix it. But let's see if file system APIs can offer us something to avoid this problem. Of course, they do. And we can create a temporary file first. And instead of writing to the target file in the cache directory, write to this temporary file. And then, once we've finished writing, we can rename it to a target cache file. This way, nobody will read from it until we finished writing. And that would solve our problem, right? Not really. The problem is that renaming a file is not an atomic operation, at least not always. And in some cases, it could be implemented as some combination of copying and renaming. And it would happen, for example, if underlying file system just does not support atomic renaming. And it's the case, for example, for a FAT32 file system. There is nothing we can do in this case. It would be nice to get some reasonable exception, I guess. But my suggestion is just don't run your web server on a USB flash drive. The second case is much more popular, and it could happen when the source and destination files are on different mount points, volumes, file system, whatever you call them. And for example, it could happen when you created a temporary file inside a in-memory mounted tempfs, and your destination file, our cache directory, is somewhere else. And this is something we can handle, and let's see how we can do that. Instead of creating temporary file somewhere, let's create it in exactly the same directory we store the cache files. This way, source and destination files will be on the same file system, so the second problem will not exist for us. Also, let's try enforcing atomicity, and in this case, we will use a special flag that our API accepts, and almost any other API accepts as well. It could have different names, but the idea is almost the same. And this will ensure that either the operation will succeed, or if the file system does not support atomicity, it will fail, and yeah, it's a predictable result. Also, there still could be a race condition when two requests will try to rename two different temporary files to the same destination files. One of them will fail, but yeah, it's not a problem. We can handle it, and it will not affect the final result. And after that, the problem was solved. I never received more complaints from my friend. So I deployed the app. And to keep the cache directory size reasonable, I set up a cron job that removes everything from the cache directory once a day. Guess what? Once a day, some requests start failing. And surprise, surprise, there's yet another race condition in the code. But this time, it's not a race condition within the REST controller, but it's a race condition between REST controller and a cron job. Here's how it works. Our app receives a request, start checking if the file exists. File was there. At the exactly same time, cron job was activated, and it decided to clean all the files, and it removed that. After that, we started reading the file, but there was no such file anymore, and we received an exception. And these particular kind of bugs have its own name. They are called time of check to time of use bugs. And for our REST controller, it's a minor inconvenience. Yeah, we were not able to read the file, but who cares, besides our users. But in practice, it's a root cause of many severe security vulnerabilities. So for us, at least, it's worth knowing how to deal with this kind of problems. And here's the solution. Of course, filesystems API provide you one of them. And instead of checking whether the file exists and then reading it, we should read files straight away. And if it will not exist, there will be an exception. We can catch and handle it, no problems. But if it exists, then we read all the data, and nobody will be able to remove the file in between checking its existence and reading from it, because there is no in between anymore. And that's enough race conditions for me for today. Let's speak about something else. As you remember, for some reason, there was a base 64 encoder. I wasn't sure why LLM generated it for me, so I asked it. And according to LLM, it's to make cache file name file system safe, even if a username contains special characters. I guess you all know what base 64 is, but here's a quick recap. It's a binary-to-text encoding. It encodes arbitrary bytes into a string consisting of letters from A to Z, upper and lowercase, digits from 0 to 9, and also dash in underscore. Two last characters depends on the configuration of your encoder, but ours use exactly these characters. So if there is some unsafe file name, the file name that will lead to a file outside our cache directory, once it's encoded, it's just a regular string that contains no special characters, and it's all safe. So let's put base64 safety, file system safety under review. If someone will smuggle some unsafe file name, username, which should become a file name, we will encode it, and it will be safe. It will point only inside our cache directory, and all will work fine. If someone else, like me, will send a safe and legit file name, like Philip, it will also be encoded, and will also point inside the cache directory, and I will receive an image, my image. But here's the problem. If right after that, someone smart will send a request with a different username, but which looks almost like mine. It's not Philip, it's Philip. Then for some reason, the controller will return my image. The image I will never give a consent to share with someone else. And that's a problem, at least for me. Why that happened? Well, that's because, yeah, base64 is safe in this context, but unfortunately, its encoding is case sensitive. So base64 encoding of strings Philip and Philip result in almost two identical strings that differs only by the case of a single letter S. And if your file systems, like on my laptop, is case insensitive, then then file names generated from both these strings will point to exactly the same file, and that's what happened. What you can do in this case, well, if you insist on using encoding for this scenario, then you can use something case insensitive, like base32 or base16, also known as hex. Or if you're a reasonable developer, you will probably use something else. For example, you can assign a unique identifier, case insensitive identifier to a username, store it somewhere, for example, in a database or in local cache, in memory cache, and use it as a file name for your cache. You can use, for example, UID as such identifier. So yeah, there were a lot of many problems for such a small piece of code. I think this was like about 10 lines of code, and we already discussed 3 problems, and it's like we just scratched the surface. So why there are so many pitfalls, and what can we do about it? So I think, it's my personal opinion, it happened mostly because there are many different policies about files and file systems. We tend to think that our applications are the only process that has exclusive access to a file system and nobody else is working with it. Or, for example, we tend to think that file paths are just regular strings, while they are not. Thankfully, modern technologies saves us from a lot of different problems caused by that, and they provide us with isolated environments where nobody else could touch the file system, or they provide us with the environments that are the same in the development cycle and in production. So we at least can test for these problems. Then also file system itself, they are complex. They consist of many different leaky abstractions on top of each other. Well, no surprise, it's complex. Abstractions tend to leak at some point. So there's nothing we can really do about that. We just have to stay vigilant. And finally, well, and that's an unfortunate part, file systems API allowed us to make all these mistakes. It was really easy to do things wrong, and almost nothing hints about all different subtleties. And thankfully, here things are getting better and better. New modern file systems API emerge. For example, you can check Zik file standard library, or you can check how wasm-vosi deals with files. And well, that's the reason I'm staying here. I'm also working with the Kotlin library team on a new, safer file system API for Kotlin XIO. So keep an eye on it. Stay tuned. And thank you so much for joining me today.